Hello students, welcome to EPG Pathshala. I am Reema Gupta from University of Delhi. Today we are going to discuss about the module Structure of Ceramics, fourth part, and it includes the structure of ionic ceramics, which is in continuation with the previous module. And this is from the paper Ceramics. So students, let us see what we are going to learn in this module. So we will be learning about simple cubic ionic structure. Then we will be learning about the structures of cesium chloride, that is CaCl. Next we will be reading about perovskites and other derivative structures. So the properties of ceramic materials, like all materials, are dictated by the types of the atom present and the type of bonding between the atoms. Moreover, it is also depend on the way the atoms are packed together. The type of bonding and structure helps to determine what type of property a material will have. So the ceramics usually have a combination of strong bonds called ionic, which occurs between a metal and non-metal, and it involves the attraction of opposite charges when electrons are transformed from metal to the non-metal. Whereas the another bond is the covalent bond. So this type of bond occurs between two non-metals and involves sharing of atoms among themselves. So the strength of an ionic bond depends on the size of charge on each ion and on the radius of each ion. The greater the number of electrons being shared is the greater the force of attraction and the force of the covalent bond. So these type of bonds results in high elastic modulus and hardness, high melting point, low thermal expansion and good chemical resistance. On the other hand, the ceramics are also hard and often brittle unless the material is toughened by reinforcement or some other means, which leads to the fracture. So students, in the following slides, we will be discussing about the structure of ionic compounds. So you can see that with different structures, they have different properties due to the presence of difference in the alignment and positioning of the atoms in the structure. So let us discuss about perovskite structures. So the perovskite structures have a formula of AbO3. They are AbO3 type of compounds. So the examples of perovskite structures are barium titanate, strontium titanate, lead titanate, etc. Such perovskite structures are mainly titanates, which happen to be technologically very useful compounds, as we will see in the later modules. In AbO3 structured compounds, A ion is 12-fold coordinated by oxygen like doctahedra, and B ions is octahedrally coordinated by oxygen ions. The oxygen atoms from a FCC-like, not FCC exactly, but FCC-like cells with atoms missing from the corners, which are occupied by A atoms. So the bond strength can be given as for cation, barium is 2/12, which is 1/6. For titanium, it is 4/6, which comes out to be 2/3. So the oxygen valence is equal to 1/6 time the coordination number of barium plus 2/3 times coordination number of Ti. So finally, we get 1 by 6 times of 4 plus 2 by 3 times 2. So the results come out to be 2. So the oxygen valency is 2. So students, we have discussed what is perovskite structure. Now you can see on the left hand side the structure of perovskite, which is AbO3 type. So as the structure tells, it has 3 types of atoms. One is A type, B type and oxygen atoms. So in the present case, the A-type atoms, which are represented by green color, occupy the corners of the unit cell, whereas the oxygen atoms, which are represented by yellow color, occupy the faces of the unit cell, whereas the B-type atoms that are represented by black in color are in the center. So this is the perovskite structure with oxygen octahedra which are formed on the faces of the unit cell. You can assume the same model as a polyhedra model for perovskite structure. So if we extend this unit cell, you can see the polyhedras at the corners which are formed. So these polyhedras are of oxygen, where we are taking A-type atom at the centers and B-type at the corners. Now let us discuss about the perovskite structure in detail. So the latest type of perovskite structure is primitive cubic. The motif is for A ion it is 0, 0, 0, for B ion it is half, 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 and for oxygen ion, that is O ion, it is half, half, 0, 0, half, half, and half, 0, half. So it has one formula unit per unit cell. So the coordination number is determined by the B cations and A cations. The B cations is surrounded by oxygen octahedra which shares corners, whereas A cation is surrounded by oxygen doctahedra which touches faces of the octahedra. So an important parameter about the perovskite is their tolerance factor. The tolerance factor is defined as T and it is given as Ra plus Ro divided by root 2 times Rb plus Ro, where Ra correspond to the radius of anion, Ro correspond to radius of oxygen, and Rb correspond to radius of B atom. This is derived for the geometry of a cube in which the atoms are of such sizes that they touch each other and hence face diagonal of the unit cell would be times the unit cell length. As a result, T is 1 for a perfect cubic perovskite. However, due to variations in the ionic radii of various ions, many perovskites show deviations from T is equal to 1 and may not even have a cubic structure. Deviation from T is equal to 1 signify the level of lattice distortion. For example, barium titanate. As we have discussed earlier, barium titanate, that is BaTiO3, is a perovskite structure and has a cubic structure. As we have discussed, AbO3 is perovskite structure. So in this case also, there are 3 types of atoms, that is barium, titanium and oxygen. So barium titanate structure, only above 120 degrees Celsius, it is cubic, while it is tetragonal at room temperature and further adopts orthorhombic and rhombohedral structure if cooled below room temperature. So the other perovskite structure types which can be mentioned in the slides are, there are various combinations of ionic valency, and perovskite can also have various combination of ionic valency, such as A2 plus, B4 plus O4, and the examples of such type are barium titanate, lead titanate, calcium titanate, strontium titanate, and so on. The other possibility is A3 plus, B3 plus O4, and the examples for this combination are lanthanum aluminium oxide, that is LaAlO3, lanthanum LaGaO3, and bismuth ferrite, that is BiFeO3. There are some other mixed perovskites, for example, lead oxide with magnesium and niobium doped. Second is lead oxide with Sc and tantalum doped. These are other mixed oxides which have perovskite structure. So students, you can see the example of barium titanate which we have discussed. So this figure shows the phase diagram, you can say, which varies with temperature. This means that the phase of the unit cell or the structure of unit cell varies as the temperature varies from 150 to 200 degrees Celsius. So you can see that at room temperature, the structure of barium titanate is tetragonal, and above 120 degrees Celsius, it is cubic. However, below 0 degrees Celsius, if we talk about lower temperatures, the structure can be rhombohedral or orthorhombic according to the conditions of the temperature. The next example is the temperature dependence of dielectric constant. So the figure shown on the bottom left corner shows the variation of relative dielectric constant with temperature. So students, one can see that the dielectric constant drastically increases or varies at a particular range of temperatures. So the points where we are seeing the random variation correspond to phase change from one to another. Now let us discuss about ReO3 structures. These ReO3 structures are representative oxides. The stoichiometry for such structures are mx3 and the lattice type is primitive cubic. The atomic positions for the M and X are, for M it is 0, 0, 0 and for X it is half 0, 0. The coordination numbers for M and X are, the coordination number is 6 corresponding to M and it has octahedral coordination, whereas the coordination 2 corresponds to X type and it has linear coordination. Such structures can be visualized as perovskite structures, which are AbO3 structures with empty B sites. Representative oxides examples are ReO3, OO3, WO3 and so on. Such oxides can be used for gas sensing and electromorphic applications. Structure of ReO3. So students, you can see 3 figures. All the figures correspond to ReO3 structure. In all the 3 cases, the red atom corresponds to oxygen, whereas the blue atom corresponds to cation. As we have discussed earlier, such structures are similar to perovskite structures, that is AbO3 with an existence of B-type atoms. So you can see in the figure that the cations occupy the corners, whereas oxygen occupy the edges. So such structures are ReO3 type structures. Now come cesium chloride type structures, that is CaCl structures. Such structures are AB or MX type of structures, and some of the examples are halides such as calcium chloride, silver iodide, silver bromide, etc. It has eightfold or cubic coordination, and the other examples for such type of structures are rock salt structured oxide at high pressures. Adoption by chlorides, bromides and iodides of larger ations also categorized in this category. The cesium chloride type structures have primitive cubic lattice, and the motifs are: for anion X it is 000, for cation M it is half half half. So it has one formula unit per unit cell. Now let us analyze the structure of cesium chloride. As we have discussed in the previous slide, it is MX type compound. So there are only two types of atom, that is M and X. Here M are represented by green color and they occupy the center position, whereas X atoms are represented by yellow in color and occupy the corners of the unit cell. So from here it is clear that the motif CS will be half 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 for M type of atoms, and for X type of atoms it is 000. So one formula unit per unit cell. The another representation is the ball stick model. There are two types of atoms, one is anion and cation. Cation is placed at the centers, whereas anions are placed at the corners. Now here comes perovskite unit based non-cubic compounds. So what do we mean by non-cubic compounds? So non-cubic compounds where the unit cell is not cubic. Many superconductors follow the structures which contain perovskite units, that is, the structure contains the perovskite structured units stacked along C-axis or 001 direction in most of the cases. So 001 direction is not necessary in every case, it can be any axis. So the examples of superconductors are yttrium, barium, copper oxide. So here Y stands for yttrium, barium Ba, copper Cu and oxygen O. So the formula for yttrium, barium, copper oxide is YBa2Cu3O7. And there are various other ferroelectrics which are perovskite unit based on non-cubic compounds like bismuth, titanium oxide. So bismuth is Bi, titanium is Ti and oxygen is O, and the oxygen is O. So the compound is Bi4Ti3O12. So there are list of many ferroelectrics and superconductor compounds which are perovskite unit but non-cubic compounds. So in some compounds such as lanthanum, that is La, strontium Sr, copper Cu, oxygen O. So lanthanum, strontium, copper oxide. The structure is composed of alternating perovskites and rock salt structural units. So in this case, there is an alternative layer of rock salt and perovskite. So it is one perovskite, one rock salt, then perovskite and then rock salt structure. So such a way of representing these structures make it easy to understand these complex structures. So here we will take the examples of yttrium, barium, copper oxide, that is YBO, that is YBaCu and O, and the next we will be taking the example of lanthanum, strontium, copper oxide, that is LaSrCu and O. Then we will be discussing briefly about these structures. Now comes yttrium barium copper oxide or YbCO compounds. The parent compound is Y3Cu3 3+O9, which also contains perovskite units. The doping of yttrium, that is Y, by barium, that is Ba, leads to structure modification as well as reduction of Cu3 plus to Cu2 plus state, and therefore resulting in reduction in the number of required oxygen ions and hence create oxygen vacancies in the structure. This gives a transition temperature of 92 Kelvin, below which the compound has zero electrical resistance, that is, it is a superconductor. And the reaction which guides it is Y3Cu3 3+O9 on doping with barium gives YBa2Cu3O9. However, when there is a reduction of Cu3 plus to Cu2 plus, the compound which is formed is YBa2Cu22 plus Cu3 plus O7 minus X. Now let us analyze the structure of yttrium barium copper oxide, that is YBa2Cu3O7 minus X. It is a perovskite structured superconductor. So this is the origin of the structure of YBa2Cu3O7 minus X as a triple perovskite unit. So you can see the reaction which we have discussed in the previous slide. You can see the modification of structure here also. So moving from leftmost corner to rightmost corner. In the leftmost corner, the compound which is Y3Cu3 plus O9 has a structure which has oxygen, copper and X valence sites. When the barium is doped in this compound, the barium occupy the centered or body center position. It replaces the yttrium. So the barium is not completely replaced by the yttrium positions. So one place yttrium is shown and the other two places barium is shown. When the oxidation or reduction occurs, so in the present case reduction is occurring when the Cu3 plus is reduced to Cu2 plus, the compound which is formed is shown on the extreme right side. Now this slide shows the atomic coordinates in YbCO compound. So we have discussed that the coordination number for CuO sheet is 5 and it is 4 for CuO chains, which you can see in this structure. So here Cu coordination number is of great interest. Cu2 plus atoms have 4-fold coordination along CuO chains, whereas Cu3 plus atoms have 5-fold coordination in CuO planes. So you can see from this figure that how the coordination number changes as the states are changes with Cu3 plus to Cu2 plus. Lanthanum strontium copper oxide, that is La2 minus X SRX CuO4. So here L is lanthanum, Sr is strontium, Cu is copper and O is oxygen. So the formula for lanthanum strontium copper oxide is La2 minus X SRX CuO4. So here X resembles the amount of strontium which is present in this compound. So the strontium is replacing lanthanum. So the amount of strontium which is present is replaced by lanthanum. That's why it is 2 minus X. So the parent compound in this is lanthanum copper oxide because strontium is a dopant. So the lanthanum copper oxide is La2CuO4, which is actually a mixture of one rock salt structure compound, that is LaO, and one perovskite structure compound, that is LaCuO3. So it can also be written as LaO dot or times LaA. So it can also be written as LaO dot LaCuO3. So the structure shows a layered structure with layers stacked as A4O, AO4, A4O as shown in the next slide, where A is lanthanum and O is oxygen. So the substitution of lanthanum by strontium results in the compound, which is lanthanum strontium copper oxide, and turning it into a superconductor with a Curie's temperature of 35 Kelvin. So students, you can see that with doping how the structure changes, and with change in structure how the properties changes. Now let us see the structure of lanthanum strontium copper oxide, that is La2-X SrX CuO4. So this structure is actually a mixture of one rock salt structure compound, which we have discussed in the previous slide. So you can see in this figure the origin of La2-X SrX CuO4 structure, and on the right hand side you can see the two perovskite unit cell which is forming this compound. So it is clear from the left figure that the top cube is the perovskite layer. So when two perovskite layers form, they form an NaCl structure layer. Moreover, you can see the two perovskite unit cell, that is one perovskite layer which we have discussed on the left hand side, and second is the layer having CuO2 and AO4 geometry. So students, let us summarize what we have learned in this module. So we have first discussed about the simple cubic packing of anions, followed by various structures which are commonly found in the literature or in nature. So the first is the perovskite. Perovskite is very common structure and it has wide range of applications. So the first is the cesium chloride, that is CsCl, where Cs is cesium and Cl is chloride. Next, we have discussed about ReO3 structures, where they are representative oxides. Next, we have discussed about the perovskite structures, which is also a repeatable unit in various anisotropic structures, such as of many superconductors like yttrium, barium, copper oxide, and various ferroelectrics like bismuth titanate. Thank you.